Please welcome to the stage, Tony Chen.
Hello, everyone. Can you hear me? Hi, my name is Tony Chen, and today I want to talk to you about what we did on Xbox One to guard against physical attacks. So the game console industry is a very funny industry. The game console is probably one of the most physically attacked computing devices humans ever made. Ever since the very first Atari game console, for decades and decades, every game console maker has had their console been hacked such that people can play pirated games. And every game console maker tried to make it such that people can't hack it, and yet they all failed spectacularly. This trend continued for decades until the most recent generation, Xbox One and PS4. So I'm proud to say that the Xbox One, which was shipped in 2013, for the last 6 years, at least we have not seen any evidence that anybody was able to break it for piracy or cheating. And today I'm going to talk about what we did to achieve that. So just a little bit of background on me. My name is Tony Chen. I'm currently a security architect at Microsoft. I've been in Microsoft for 22 years. Most of my career is working on Xbox Live. And during the period of 2011 to 2013, I was the dev lead for the team that developed all the software for security software related to the Xbox One. And that's why I'm presenting this. So let's start with the goals we want to achieve here. What do we want to do? Well, it turns out there's two very unique business goals to the Xbox console business. One is we want to prevent the piracy of games. This is absolutely critical to the entire business. The whole game console industry works on a razor blade model. We sell the console literally at a loss in order to see the market with a lot of consoles. And then we recoup the money as games are being sold. If people can pirate games, we're basically subsidizing the world with low-cost computing devices. And we would stop making Xboxes and get out of this business if that happened. So the fact that we need to stop piracy is fundamentally critical to the business. It's not a nice-to-have feature for the Xbox. The other is cheating. The previous talks gives you a very good sense of what happens with cheating. We also want to stop that on Xbox because people want to be God when they play with each other. We want to build up Xbox Live as a cheat-free environment where people can play fairly and win based on the skills on your fingers instead of your hacking skills. So what do we technically need to do to achieve these goals? Well, the most important thing is we have to maintain control of the CPU. And we have to make it sure the CPU only runs code that Microsoft signs and keeps on doing that. And the important thing is we have to do this against the wishes of the Xbox owner. Unfortunately, the Xbox owner is the person that wants to pirate games and cheats. So he is going to physically attack the device in order to achieve the goal of taking over the CPU. And that's why we have to guard against physical attacks. Besides that goal, we also need to prevent the disclosure of the plain text games, keep it secret for as long as we can. And the third point is just that we've realized both in the original Xbox and Xbox 360 generation that we will make lots of mistakes, software mistakes. And we have to be able to recover from these mistakes and get ourselves out of that world. So we have to be able to recover from it. So one thing I just want to briefly mention is that when I joined the Xbox world, there's a lot of people from the Windows org that also comes, and I always have to explain to people why the fundamental problem of Xbox security is different than Windows security. To most people, both contain the word security in it. It's got to be the same problem. The problem is completely different. So for Windows security, the problem is the PC owner is working with us, Microsoft, the OS vendor, to guard against bad guys out on the internet taking over their computer. For Xbox, the owner is the bad guy. So you fundamentally are selling this piece of hardware to a bad guy, and you have to treat them as if they were malicious when you design the system. The consequence of this is that you pretty much can't trust anything exposed on the motherboard, whether it's flash, the hard drive, the optical disk drive, even DRAM. Everything exposed on the motherboard is fair game, and I'll talk a little bit about how we designed this whole thing based on such a model. So before we get there, though, I want to go through 2 examples just so that you get a flavor of what people actually do to hack game consoles. Both of these examples happened on the Xbox 360. So the first one is called the kamikaze hack. So let me set some background here. One of the ways people pirated games on Xbox 360 is instead of trying to break the CPU, they broke the optical disk drive controller. They basically modified the optical disk drive controller to lie to the CPU and say, hey, I got a genuine piece of plastic in my tray right here. It's not burned plastic, trust me. Let the guy play the game. By doing that, they already achieved piracy because everybody can just burn their own disks and you're done. And so we fought this problem very early on, and the fundamental issue is that we had 2 separate chips. There was the optical disk drive DSP chip, and there was a flash chip. And because of the technology, these were 2 distinctly separate chips. So the flash chip was exposed on the PCB board on the optical disk drive, and people can just clamp something onto it and reflash it with different code. So one of the first ideas we came up with, well, what if we package these 2 things together on the same package? So if you look at the picture on the upper left, that's basically what we did. The smaller chip die on the top is the flash chip. The bigger die on the bottom is the DSP chip. We basically programmed the flash, we put it in the package, we grounded the right enable pin on the flash, and then we packaged this together thinking nobody's going to touch this. The flash is sealed in there, it's already written, nobody can change it. So what happened? People started selling this kit on the lower right. And this hack is called the kamikaze hack. What this kit does is you use the funny looking thing on the top to draw these lines on the chip to pinpoint an exact position. And what is this exact position? The exact position, if you drill into it, will lead to the right enable pin on the flash chip. So then what you do is you take that stick, you start at that point, and you connect the wire through an LED light to supply voltage. You keep on digging deeper and deeper until the LED light comes on. That means you hit the right enable chip. And the voltage is supplied to that pin, and at this point you reflash the flash because it's enabled right now, and with a different firmware, and you're back in game again. You can lie to the CPU about whether you have a genuine disk again. So people actually bought kits like this and did work like this on their Xbox, just so they don't have to pay $60 for games. So this is what we have to battle against. So the second attack I want to illustrate is the reset glitch hack attack. This happened very late in the Xbox 360 cycle. By the time we found out there was this bug, we already made 50 million consoles. So it was kind of game over. So what happened here is they found out that if you glitch the reset pin to the main PowerPC CPU with just the right amount short pulse, not too long, not too short, you made funny things happen in the CPU. It didn't really reset, which is what it's supposed to do. It's kind of just crashed. And the crash means something funny is going on. And they try to see, well, if we make this funny thing happen at different times, what will happen? So they kept on experimenting for half a year, just trying all kinds of things. And they finally nailed it down perfectly to do this exactly when we were doing the mem compare between the SHA digest of the first stage we're about to load versus the SHA digest that the signature is signed. We do the mem compare, they glitch us exactly at that time, and they make that one if statement go down the wrong path, and thus load their own random code, their own unsigned code, and make the system boot into that. And you can see that this mod chip board is a little bit more complicated. It actually does a lot of things because they had to do a lot of things to actually achieve that. They first had to hack the Southbridge chip because the Southbridge chip controls the voltage and clock of the main CPU. So they wanted to lower the clock of the main CPU while this attack was happening because it's easier to get the timing better when the clock is lower. Furthermore, even with that, they only had a 1 in 3 chance of getting the boot to work. So they programmed the south switch to just do a loop, just keep on booting until eventually it worked. So this came out, and it pretty much ruined the scene for Xbox 360, at least for us. Fortunately, it was at the very end of the cycle. At that time, we were already working on the Xbox One and getting ready to launch it. But again, this is an example of what people do to break game consoles. And we need to design Xbox One based on assumptions people are going to do things like this. So let's start talking about what we did with hardware security. So what is the fundamental, like if we can't believe everything on the motherboard, what can we believe in? Well, the fundamental model we end up with is we think it's still too hard to break into a 28 nanometer die and do something funny within that die. Everything funny the hackers do, it's outside of that. So we basically start with a simple rule that we can trust this CPU die, but nothing else outside of it. So when we say we can't trust anything else outside of it, certainly all the JTAG pins, the clock, voltage, they'll all be manipulated. The DRAM bus is also outside the die, so it can be manipulated. And certainly anything in PCIe, SATA, USB, all of that has to be treated as totally malicious. So, and then we surveyed the PC hardware space. It's like, is it possible to buy anything that's designed to deal with this? Most PCs, DRAM is not encrypted or protected. And so like in typical Intel chips, they actually build a lot of their security features in the south bridge, which is a separate chip than the main CPU, and there's an insecure bus between these two chips. In fact, what Intel, the first thing an Intel chip when it boots up is it reaches out through this exposed bus and asks the south bridge chip, do I need a secure boot? And if the answer is no, it doesn't secure boot. So it's really hard to take an existing chip and try to build something secure here. TPM, similarly, a lot of people are familiar with TPMs and using it to measure stuff and achieve security. It totally doesn't work against these hackers. It's a separate chip. The bus between it will be hacked. All the measurements will be fake. So we had to basically, we reached a conclusion that we have to build a custom chip to solve this problem. Fortunately for us, in order to build a game console, you need to build a custom chip anyway. So that part made it easy. But we tagged along extra security requirements, and we worked with AMD to build a custom chip. So this is what the hardware design looks like from a security perspective. The big square you see there is the SOC. So you can see a security complex on the bottom there, where we added an extra security processor. These are typical things that do not exist on the AMD CPU. We added custom crypto engines and registers, random number generators. We have some secure RAM. We have secure ROM to boot the system from our own bank of fuses and side channel monitors to monitor the voltage, temperature, clock, all those things. On the right, you see the memory controller that connects to the DRAM. We customize the memory controller to add encryption and integrity checking because we don't want to trust DRAM. Of course, we have the CPUs and GPUs inside it. On the left, we have the south bridge, which is basically a PCIe interface connecting to the south bridge. And of course, everything on the south bridge is totally untrusted, including flash memory, the hard drive, and everything like that. So we have to use the IOMMU to protect everything that comes out of there. And then you'll see this streaming crypto engine that we put on the upper left there. It's a custom engine we also added in order to do high-speed crypto and SHA-hash verification of everything we read from the hard drive or optical disk drive. We basically, because we cannot trust the data there, we have to verify everything we read from there, and we want to do it in I/O speed. We need a custom crypto accelerator. And you'll see a special line from the crypto engine feeding into the streaming crypto engine, where we literally have a dedicated hardware path for keys to traverse from this component to that component without using the general fabric of the CPU. So Let me talk through what are the core tenets of the design and then what are the core things we wanted to achieve. And I'll go through each one of these bullet points in more detail throughout the talk. So first, I just talked about it. We added the security complex with the security processor to kind of orchestrate the overall SOC security. That turned out to be a very important and critical aspect of what we did. We believe in defense in depth. You have to make the attacker go through multiple stages. Don't trust on any one stage being secure. We keep all of the OS in the games encrypted everywhere except inside the SOC die. So literally, if you take apart an Xbox One, you look at the flash, you look at the hard drive, you look at what's on the optical drive, you look at DRAM, everything's ciphertext. You can't figure out what's going on. You just see a bunch of ciphertext flying into the CPU, and yet a game shows up on the screen. That's for the perspective of the hacker sees, and we like that. So the keys to decrypt the games will only show up on your console if your game is paid for. So a lot of DRM rules that you have to do checks and say, oh, if this condition, then I'm going to let you execute this code or whatever. For the games, I basically wanted to enforce that if you didn't pay for it, the plain text version of your game is never going to show up inside your CPU. And if you can't make the plain text game show up, you're certainly not going to play it. You can't play the ciphertext version of a game. So then this is one of the core tenets. We have to maintain control of the CPU in a very, very strong way, and we'll talk about how we do that. The CPU can only execute Microsoft signed code. No exceptions, no nothing. And we want to make it such that malware can never persist itself on an Xbox across a code reboot. We keep the development key world and the retail world separate. So a development kit is basically what we have to give the game developers. So the rule where we insist the CPU only executes Microsoft signed code, obviously we have to loosen that rule for a dev kit that we give the game developer because they're going to write their own game and they can't bring it to Microsoft to sign just for each iteration. So we have to loosen the rules on CPU execution for the development kit, but we don't want these things to become the things that is used to break the games of the retail world. So we did something to make sure that doesn't happen, and I'll talk about that later. So security booting the system is kind of the root of how all this works, and it must be extremely strong. We'll talk about how we did that. And finally, we have to attest and recover from any software mistake we make in it. And we know for sure we're going to make lots and lots of mistakes, and we have to be able to update, fix it, and the update needs to be absolutely, we know you are running the version that has the bug. You're not tricking us. You are going to get updated, and then you get to play the game. So let's first start with the security processors. Well, what is the goal? What does this thing do for us? So first, it orchestrates the secure boot for the entire SOC. This is very critical. It manages all the keys to decrypt the OS, the games, and things like that. It enforces the DRM policies of it. The DRAM encryption keys is programmed by the security processor. Whether the console functions as a dev kit or not is controlled in this. It uses fuses to prevent rollback to older, buggy versions of software. And it manages the clock and voltage of the entire chip, and it resets if anything goes out of range. So let me explain a little bit the multi-VM architecture we have on the Xbox One. So we actually have a hypervisor on it, and we're actually running multiple virtual machines on the Xbox One. We didn't really do this on the Xbox 360 or the earlier Xbox. We started doing this on Xbox One. And you can see that at the very bottom, we have the security processor, and then the hypervisor layer, and then there's a host OS that contains all the bare metal drivers to talk to hardware. And then we really have two main operating systems operating on top. The game OS, which is the VM that actually runs your actual game. So Halo and Call of Duty actually runs there. The system OS is just a version of Windows 10 that does more the traditional dashboard menus and things like that. You know, the more traditional stuff when you pick which app you want to run and things like that. So the reason we did this is this actually enforces the defense in depth notion. When we threat model this, we basically assume system OS is already compromised. Just forget about it. Like, the bad guys are going to get in there immediately. It has a browser, you're done, okay? So, but even if you compromise system OS, in order to cheat or do anything, you have to get yourself into the game OS. And so you most likely have to find a hypervisor or host OS bug to reach into the game OS. But that just allows you to cheat. If you want to pirate games, you have to break all the way into the security processor, which you have 2 more layers to go through before you even get there. And this reinforces the notion of defense in depth. So let me talk about Xbox virtual disks. The idea here, so here's the fundamental problem. Most operating systems designed in the world right now make the following assumption. If you write a sector to the hard drive, and you later on read that sector back, you're going to read the same thing back. On Xbox, you can't make that assumption. That's not going to be true, because you're going to be fed back the most malicious, worst data possible. And you have to make that assumption on every single disk read you make. So what we did is we created our own virtual disks. Think of it as a VHD that's integrity protected and encrypted. And these VHD files is what's actually sitting inside the hard drive. So you can see the layout of one of these XVD files. On the right, you literally have the virtual disk laid out, and then you have a hash tree that stores the hash value of all these things, and a header that signs the root hash value. By doing this, we can integrity check every single bit read from this entire thing. Not a single bit that can happen without us knowing about it. So this is how we guarantee the integrity of all the data we read from the hard drive, because we can't trust it. So let's talk about license key packages. So like I said before, all the games are encrypted. And in order to play the game, you have to get the key to decrypt the game. So we actually, through Xbox Live, can distribute these license key packages. They are customized for each individual Xbox. The license key package will only be given to you if you pay for the game, and only the security processor on your console is able to unwrap this license key package and derive the key to decrypt the game. And then what happens is the key gets passed along to the streaming crypto processor we talked about earlier, and that's actually used by the host OS to decrypt the game on the fly as each sector is being read by the game. Now, throughout this entire process, we've designed it such that the key to actually decrypt all these XVDs and the game is always locked in hardware. No software ever gets access to it, whether even the security processor software. The security processor, even if it has a critical bug, cannot leak out the key to decrypt any Xbox One games. It's totally locked in hardware. So I want to talk a little bit about optical disc games. This is a pain in the neck for us. And on Xbox 360, we talked about the kamikaze hack. It basically exposed us to piracy on Xbox 360 due to weaknesses in this area. So the fundamental problem is that we're trying to use the optical disc not just as a means to deliver 50 gigabytes of data. It's very good for that. But we're also using it as the means to represent the license to play the game. So this means that we face a bunch of hard problems. So first, how do we know you have a genuine piece of plastic? We have to design this piece of plastic such that it's very easy for us to make 20 million copies of it, but very hard for you to burn one of these yourself, such that you can pretend to be one of these things. Then even if we solve that problem, there's the problem of, well, the CPU doesn't know what's over there. The CPU just has a SATA drive connected. It has no idea what's really on the other side of this SATA drive. It has to kind of believe the thing on the other side of the SATA drive, and that thing's going to tell me, oh, there's a good piece of plastic there. Why don't you let the guy play the game? So you can see there's lots of problems in this whole thing. What we did for 360, we already did some stuff. So we set up a shared key between the security processor. Well, on the 360, there wasn't a security processor, but it was the hypervisor there. But we set up a shared key between the CPU and the optical disk drive, and we pair them together at manufacturing. And this shared key is used to authenticate each other. And because of this pairing, if you notice, if your optical disk drive on your Xbox One breaks, you can't just swap it with the optical disk drive on another Xbox One. You have to send it back to Microsoft, and Microsoft has to repair these two things together. But the biggest problem we face in Xbox 360 is the fact that the DSP chip itself was an off-the-market DSP chip with not enough good security. So we've had to solve that problem for Xbox One, and what we fundamentally did is we basically worked with MediaTek to say, make us a custom DSP chip. The one you have just isn't going to work for us. And so just like we made a custom AMD chip for the main CPU, we make them make a custom chip for us for this optical disk drive, and we added security features into it. And we personally authored all the boot code on this chip and made sure it was correct. And that's how we finally stopped the optical disk piracy problem. Let me talk a little bit about hypervisor enforced code integrity. Like I said, one of the main things we need to do is maintain control of the CPU. It's very, very important. So we have to make sure only code we sanction gets to run on this. But the traditional way this is done is kernel mode will do code integrity checks. But there's millions of lines of code in kernel mode. My rule of thumb is you write that many lines of code, it's hopeless. Like, you're done with. Like, it's guaranteed to have lots of bugs. So we have to move enforcement to a layer that has fewer lines of code and a higher chance of being correct. To us, that was the hypervisor. And so what we did is we made the hypervisor enforce code integrity by controlling the second stage CPU MMU to only light up pages to have execution permission if the hypervisor personally verifies the SHA hash and agrees that this page is a correct Microsoft signed executable code page. And throughout this entire design, we basically treat supervisor as malicious and don't trust anything from the supervisor. And supervisor has to beg the hypervisor, please let me execute some new code. It can't do it by itself. So this feature, we call it HVCI. This term sounds familiar. It's actually part of a Hyper-V feature now in Windows. And we recently announced the Secure Core PC effort. And there's a bunch of security features in there. HVCI is one of them. But this whole idea literally started on the Xbox 360 and continued on Xbox One. And that's the origins of why we do this. So I want to talk a little bit about the state separation and integrity checking we're doing. So because we did this XVD thing for an operating system, we naturally do something great here, which is at every boot, we re-verify every single piece of code we execute that we read from the disk. We don't trust anything. And by doing this, we actually achieve a very important goal. The consequence, I call this consequence, malware cannot persist across the code reboot. Because every time you code reboot, you start from fresh again to execute code that you personally verify every single boot. There's no way for malware, unlike on a Windows PC where there's various ways it can hide itself in various places. There's no way on an Xbox for malware to persist itself. And this is very, very critical. And at least on a console, what this means is that if you find a way to break it, you have to break it every single boot. You can't just break it once and you're done. And so this, again, puts a roadblock in front of the hackers. So I want to talk a little bit about the custom security processor key registers we have. I've touched a little bit on it. But in this custom security processor, we have custom registered to do the following things. First, we have a hardware PCR. For those that don't, PCR is platform configure register. It basically measures all the measurements that the system boots. But we have a custom hardware-based PCR that takes measurements, and then we use it to perform attestation to Xbox Live. We have a key dedicated to maintaining global secrets. We have a key dedicated to maintaining per console secrets. And we have key slots dedicated to maintaining the keys to decrypt games and things like that. And through this custom key register, we achieve a lot of wonderful goals. First, I talked about it is that all the important keys are never accessible by any firmware whatsoever. Firmware only gets Oracle access to keys. And second, we'll talk about this more later, which is the keys can actually change based on what you booted, and we can make the system, we can actually make the system have new secrets depending on what you booted. If we update the system, you'll have a new secret that you didn't have access to in the old world. So this is how that works. So the global key, we start with the root key at boot time. And as the system boots, it morphs down into different keys. And we destroy the original key as it morphs. So you lose the original key. So if you're booting version 3 of the security processor software, you go down a certain path, and the global key now becomes this value. And then if you boot the retail console, retail path, it goes down a certain console, and then the version of the OS you load. This is a gross simplification. We probably have like 10 layers of this instead of just 3 layers. But this makes it such that you go down a different path depending on what you booted. And notice that whether you're booting as a dev kit or retail unit also is a different path. What this means is that when you boot, if you boot as a dev kit, your global key will morph in a certain direction such that you will no longer ever be able to decrypt any retail games. Like you lost that capability. You don't have the key material to ever do that again. And that's how we guarantee dev kits can't compromise the retail world. But you can see this is very this whole construct is very powerful because as you move down these things, typically people find bugs in very later stages of the software. The early boot stages, it's harder to find bugs. Later stages find bugs. But all we have to do is update the software, and we change you to a different key, and the attacker can only see the keys that he has access to in that old world. In reality, what this means is he will probably be able to decrypt all the games released up to that point, but he cannot decrypt any games going forward. We'll update the system and release new games to only be decryptable by this new global key path. So secure boot. This is one of the areas we spent a lot of time on because we know, at least in the game console industry, this is what the attackers always go for first. So first, one of the most important things is we have to have private SRAM inside the security complex. We need to read the next stage bootloader from flash, bring it into the die that we can trust, and then verify everything, and then jump into it. A lot of secure boot have the policy of using being exploitable like time of check, time of use bugs, where you read it 2 times. The first time to verify, the second time to actually execute. The hackers will make the first time look correct, the second time look bad. So you can't do that. We also measure everything we boot into the hardware PCR that we talked about later. Every single stage is encrypted, and the decryption key is based on the global key tree we talked about. So the global key tree, it keeps on morphing, and you actually need the global key tree to decrypt every single stage in this whole morphing process. So there's a bunch of consequences to this. If you ever change 1 bit in any one stage, you will basically go down an incorrect path, and you can't decrypt future stages. Also, if you ever get to a certain stage n, the system has already lost all the keys to decrypt all the previous n-1 and earlier stages. You can't go back and decrypt all the earlier stages. You just decrypt the stage you broke. We try to design it such that because of the reset glitch hack, we made sure there's no single one branch in the boot ROM where if we go down the wrong path, the system will do the wrong thing. So example of this is when we take the measurement of the next stage that comes in, typical people will SHA-hash the measurement, look at what's the digest that's been signed, compare the two like we did in Xbox 360, and then decide, oh, these two matches, and use this digest to do something. What we do is we load the next stage, we SHA-hash it, and before we even know whether this is the right digest value or not, we extend this hash digest into the PCR, and we also morph the global key tree using it. So after we did that, it's a done deal. Like, if we find out you're wrong based on the check, everything, the rest of this entire boot sequence is going to be completely incorrect. And so you cannot glitch, a single glitch cannot get you out of this bad state. And we use this kind of philosophy throughout the boot ROM code. We also made the security lock processor lock down all the security processor code after boot. So literally, the security processor, after it boots, it throws away all the keys to add more code. So it can't add more code even if it wanted to also. So this just makes it, obviously you can still do a ROP chain attack, but it makes it harder for an attacker to do more sophisticated stuff. So finally, we did Attestation to recover from software mistakes. This is absolutely critical, and I'll talk about it later. But what it fundamentally means is that we have to measure everything that's booted. The hardware PCR we talked about earlier, literally the ROM code measures the first stage measures the second stage. All these measurements are extended into a hardware PCR that cannot be undone. And then we literally have a custom private key that does nothing but sign this PCR register to perform attestation. And so by doing this, we can pretty much guarantee that attestation is accurate even for the very first stage firmware. So even if we have a bug in the very first stage firmware, we can recover from this bug, and that was critical for us. The corresponding public key associated with the private key used for attestation, we seal in the console certificate that we make during Xbox manufacturing time, and that certificate is presented to Xbox Live whenever we need to attest an Xbox console. So pretty much because of this, we can recover from any software mistakes made in any firmware throughout the system. The only place we cannot recover from software mistakes is if we wrote a mistake in the boot ROM. And that's why we had to be really careful with that. So, why has Xbox security lasted so long? Like, my view of what we did right to make this successful? We did a few things right. So first, the fact that we created this separate security processor and security complex, it helped us out a lot. It made secure boot really possible without worrying about side channel attacks and all kinds of things. And the custom crypto registers to keep keys secret, it also helped a lot. Second, we try to keep everything as simple as possible. Like the boot ROM, it does nothing but load the next stage and jump into it. Anything related to setting up hardware, if we can defer that, we defer that to the next stage. The boot ROM has to be as simple as possible. The security processor code, we make it as simple as possible. There's literally no OS in the security processor code. It's just a dispatch loop. The hypervisor, we make it as simple as possible. The one used on Xbox is not the full-blown Hyper-V that's used in Azure. It's a much more trimmed-down version. The fact that we have all the code encrypted, we believe it gave the attackers a hard time. Like, we don't know how far the attackers got, but the fact that everything's encrypted, that every single stage of boot code, all the games, all the OS, everything's encrypted. All you see is ciphertext. I have to believe certainly slowed them down. Like, they have a hard time just decrypting things to begin with, and you have to decrypt it before you can start attacking it. We did lots of careful reviews, threat modeling, penetration testing to avoid making any stupid mistakes. And lastly, this part I think is really critical. The fact that we do the attestation is very critical. If you think about it from an attacker's perspective, if he finds a bug in our code that enables piracy or cheating, what is he going to do? So he can announce to the world, oh, Microsoft has this bug. And what's going to happen? Microsoft's going to patch it tomorrow. release an update, everybody in the world will get updated, and he did all this work for nothing. It's useless, okay? So if he thinks about it, he say, if that's the case, why am I going to bother attacking this thing? It's useless. Of course, I can attack it so that I personally can cheat and pirate, but the fact that I can't announce it to the world and become a glorious person, it's very unsatisfying. So, and because of this, people tend to not spend the time to attack us. This is my view of what's happening. And I think there's something like this also happening for the PS4 also. Pretty much the only thing they can attack that is permanent is if they find a bug in the boot ROM code. And that's why we spend so much energy on that in hopes that there's no bugs there. So what are the key takeaways here? The first I want to say is just existing hardware is typically not designed to be resilient against physical attacks. Everybody should remember this. Like, don't have dreams that you can just go out and buy some kind of PC and it'll be resilient against physical attacks. We're so far away from it. DRAM's typically not encrypted. The fact that Southbridge, TPM, Flash, all these things are exposed, it's all the problem. Some industry standards are literally defined to be insecure. So I bring up this example of address translation service on PCIe. The first time I heard of it, it just baffled me. It just shows that this industry emphasizes performance over security. So what this is for those that don't know, is in PCIe, there's the way to speed things up. You typically go through an IOMMU. The PCIe peripheral says, hey, I want to access this virtual address. The IOMMU does a lookup, looks up the physical address, checks to make sure you have access to this, and then returns the physical address along with the virtual address back to the PCIe device. And the next time, the device can come back with just the physical address and say, hey, trust me, I remember the physical address from last time. Just directly let me DMA right here to this physical address. Don't look up your IOMMU. Everything is good. Just let me DMA right here, and you'll be fine. And if you follow this standard in PCIe, you are building a device that is, by definition, always physically attackable, because the PCIe peripheral can just trivially attack you. Obviously, we turned this off for Xbox One, but I just want to illustrate there's lots of designs like this in the industry where the trade-off is always performance over security, and that saddens me. Also, keep in mind existing software is typically not designed against physical attacks. The fact that we can't trust the hard drive, most operating systems are designed assuming the hard drive will reliably remember things for you. Most systems are designed assuming nobody can clamp something onto the flash and reprogram it. They assume that if software blocks access to flash, that's good enough. And then another key takeaway is the fact that we add this security processor. It really helped us orchestrate the SOC to be more secure. Looking back, that was a really great decision that we did, and we actually strongly encourage the industry to move in this direction. And finally, I want to say that building this was not easy. It took a lot of hard work, a lot of careful thinking, but we have proven that it is actually possible to build a device that can withstand a physical attack. For most devices, you could build it and you say, well, nobody attacked it, I guess it's secure. That might not necessarily be true. For a game console, after you build it, if nobody can attack it, we know for sure people have tried attacking this thing. So we can say that it really is secure. Finally, I just want to say that although this sounds like just a Microsoft project that helped make the game console secure so that we don't have piracy and cheating on Xbox, this whole project, which we finished in 2013, actually influenced the industry in various ways that might not be obvious. So we were the first to do DRAM encryption. We've been pushing Intel and AMD to also do this. Now that's a feature that's coming to their chips. The fact that the security processor is being added, basically this project happened in 2013, and afterwards AMD added a PSP, platform security processor, to all of their CPUs going forward. It was highly influenced by this project. And also, some of you may not know, there's an IoT Azure Sphere project that has this secure Pluton core. Well, the Pluton core came from the security processor. It was derived from the Xbox. So this Xbox project created a lot of technology that was used throughout Microsoft. We also talked about HVCI, and is influencing the industry in various ways. So it's quite, not only is it successful for the Xbox business, but it affected the industry in various ways, and we're very happy about it. So that's my talk. Thank you very much.